Alright, so this is the unit that isn't in the online textbook, but that's okay because I've posted readings on Canvas, and so we should be okay with that. So, differential equations. It sounds kind of daunting, or it might not because it just sounds like you have a different kind of equation, but differential equations is pretty cool. It's this is like a whole nother class after you get through, like, your first pass at calculus. There's differential equations, there's different kinds of them, there's ordinary ones, and then there's partial differential equations. But for now, we're just going to look at, one variable, well, two variables, but one variable that's changing. And so it's like pretty okay. Like, we can handle this. That's what I'm trying to say. We can handle differential equations. If you just start Googling some of these things, though, it might get kind of crazy because, again, there's just this whole field. There's multiple courses that you could take on differential equations, ordinary ones, partial ones. There's so many things. But we're just going to start looking at things, and yeah, I really like differential equations, though. They're really cool. And once you know, so once you know more about like matrices and how to use those, then there's even more exciting things, because like once take linear algebra, it'll be great, and just keep on taking more math classes. It's fantastic. Yeah. Alright, so, but differential equations is, this rant about differential equations is going on a really long time. It's really exciting because it helps you examine things and model things as they're changing with respect to how things are changing, not necessarily like the actual values, because you can extrapolate more information by how things are changing. And so this has applications everywhere. It's like weather models, looking at, I think it was probably utilized, well, in like any sort of, space travel kinds of things. And there's, applications in population models, thinking about carrying capacity. These are all things that utilize differential equations. So here we go. It's very exciting. So slope fields, that's the first thing that we're looking at. We're going to look a little bit at Euler's method. There is a video clip. I hope it works. We're going to look at solving differential equations, which is not super complicated right now, and some applications with Newton's law of cooling, which you might have seen in some of your science classes, maybe. And if not, then it's okay. We will look at it. Well, that was loud. Okay. So the first thing that we need to do is just figure out, well, is what's proposed, these A, B, and C solutions, are they solutions to this differential equation? And differential equation just means that we're looking at derivatives, and it's grouped together in an equation. So here we have a second derivative, right? Well, y double prime minus y, which is no derivatives are taken, but that's the function. And that equals 0. So we have derivatives happening, so that's the differential part, and we have an equal sign equation. So how do we determine if a function is a solution to the differential equation? Well, step one, we're going to take the first and second derivatives, because you can't take the second derivative without finding the first derivative, right? Because you need to take the derivative of the derivative to get the second derivative. And plug those in to the given differential equation, see if it's true, and if it's true, then yes, that is a solution to the differential equation. And if it's not true, then no, that is not a solution to the differential equation. We're just seeing if y works. And this is very similar to how you started solving equations when you were, like back in, I don't know, however long ago it was that you first started solving equations. You just plug in numbers and see if it works. Now, the input that we have isn't numbers, it's functions. But we can handle that because we've been doing this for several months now. So, let's look. For part A. Oh, I want a highlighter. I don't want a highlighter. Okay. So for part A, we have y equals sine of x. So our first derivative, y prime, is cosine of x, and our second derivative, y double prime, is negative sine of x, and the reason for the negative is because the derivative of cosine is negative sine, and let's plug that in here. So what do we get? We have y double prime minus y equals 0. Is that true? Not sure. Let's plug in y, oh wait, no. So let's plug in y double prime, and we get negative sine of x minus y, which is sine of x, and that equals negative 2 sine of x, which is not 0, therefore no, y equals sine of x is not a solution to the differential equation y double prime minus y equals 0. Alright, so try B and C on your own and see if you can find whether or not those are solutions to our differential equation. So for B, we're going to take y is 4e to the negative x. Take our first derivative, y prime is negative 4e to the negative x because of the chain rule, and y double prime is 4e to the negative x because negative negative is positive. And y double prime minus y, what is that? 4e to the negative x from there, minus 4e to the negative x. 4e to the negative x, which equals 0. And that makes our, that satisfies our differential equation. Therefore, yes, y equals 4e to the negative x is a solution of y double prime minus y equals 0. And notice that we're saying a solution because this is not unique, the solution for a differential equation. All right. What about C? We're just looking at that. C, for part C, we know that y prime is going to be ce to the x. We know y double prime is also ce to the x. So from there, we can just see, we can just see that our differential equation is satisfied, that y double prime minus y in, for y equals c times e to the x totally works. So yes, absolutely. For part C, yes. I wonder if e is going to be, e to the x is going to be like super handy for a lot of these. It is. Alright, so can you try to match the vocabulary words to the appropriate equation? It might have helped if you, number one, have any physics background, number two, read the book, or read the reading. So match. Which one is an initial condition? Initial condition means that that's something that we've plugged in. Let's need to move these over. So which one of these is something that we've plugged in? Well, s of 0 equals 80 and s prime of 0 equals 64. That seems like an initial condition to me because we're given initial values. What about general solution? General solution means that we don't have only coefficients that are numbers, that we have a more generalized situation happening. So the general solution is our s of t, because that's going to be our solution, but we have coefficients of c1 and c2, and these are coming from integrating a couple times. So be very careful. We need to be very careful when we're integrating things that are higher order derivatives, that we might have different c values, and we need to make that distinction with subscripts, which is our favorite thing to do. As mathematicians, we love subscripts. They really help us because then we don't have to make new variables. We just take the same letter and then add a number to it, and that's great. Let's see. Our differential equation is our equation with our derivatives, right? Which, this one's really simple. Our second derivative is equal to negative 32, and that, I think that's a gravity constant. Acceleration due to gravity in like feet, I think? Feet per second? Sure. Something like that. And then that only leaves our particular solution as s of t equals negative 16t squared times 64t plus 80, which looks very similar to our general solution. However, we have values for our c sub 1 and c sub 2. So we're no longer looking at a general solution of a family of functions that are all parabolas, right? These are all parabolas, but they have different roots or different solutions. And then this is our particular solution utilizing our initial condition. So can you see that if you plug in 0 to s of t in our general solution, but you make sure that it equals 80, that we get our coefficient there. So let's see. If we have s of 0 equals 80 as an initial condition, then s of 0 when we're evaluating is negative 16 times 0 squared plus, that's a C, not a 6, C1 times 0, which by zero product property is 0, and then C2. So 80, which we're getting from here, equals 0 plus 0 plus C2. Therefore, C2 is 80. And the same deal goes for using our first derivative. If we take our first derivative of this general solution, plug in our initial condition, then we can get our particular solution given this initial condition. But we will get to that a little bit later. Alright, so look at these slope fields. Slope fields are fun because instead of looking at a particular curve, we are looking at the general behavior of what a function would do with our differential equation, what those slopes are going to be. And so you get these little tiny lines, and these tiny lines are called isoclines, which is really cute. I think the tiny lines are called isoclines. Isoclines. But they're tiny slopes, and one of your best tools for doing these kinds of problems, I really think, is just having some sort of pencil in your hand and just following curves. Just like how we used to use, like a little penguin for thinking about increasing and decreasing. Just use a straight thing and use it to envision what curves are going to be. It's really, really helpful. So, thinking through these slope fields where at a particular location we're going to have a slope that is something. So at the point 0, 0 for A, let me use the mouse that you can see. So at the point 0, 0 for A, we have a slope of 0. So which of our differential equations out of Roman numeral 1, 2, and 3 would give us, if you plug in the point 0, 0, you get a slope of 0? Well, it's all of them, right? Because if you look at the origin for B and you look at the origin for C, all of those are zeros. So, maybe we need another tool. Well, you can think about, if you look at the slope fields, if you look at this one, all of the slopes on vertical lines are the same. So, no matter what output you have, no matter what y value you're plugging in, your slope is going to be the same. So for A, this does not depend at all upon the y value, only the x value. For B, it seems like if you're looking vertically, those are all changing. If you're looking horizontally, those are all changing. So this seems to depend on both x and y. And for C, if you look at it, if you're going across, you have the same slope. You have the same slope for all of these isoclines, no matter what x value you're plugging in. So, with that in mind, well, if A, the y value doesn't matter, that means that this looks like it's going to go with 2, where we have y prime equals x. And let's see if that makes sense. Well, 0, 0, yeah, that makes sense. At 1, our slope is 1, yeah. At x equals 2, our slope is more steep. At x equals -1, our slopes are -1s. Yeah, that makes sense. That's good. Okay. So we check this off, because that's a good test-taking strategy of crossing things out once you've finished with them. For B, we know that this is going to depend on both x and y. So the only option that we have is let Roman numeral 1, where we have y prime equals x plus y. And let's just think about that. So if we have x values and y values are both positive, then the sum of those is positive, and we're gonna have positive slopes. So our isoclines in this quadrant are gonna be positive. Whenever our x and our y are the opposites of each other, so they're on the line y equals -x, then our isoclines are zeros, and that makes sense, along this line right here that I just sketched in, then you can see that the isoclines are all slope of 0. And as we're looking at the negative numbers, negative plus negative is going to be more negative, so we have negative slopes all in our third quadrant. And so these are all just other ways that you can think about what to do. All right. So that's for part B, and then let's check that off. And then C, that just leaves C where we have y equals our slope. And and y prime equals y. And does that make sense? Well, whenever our y is 0, our slopes are 0. Whenever y is 1, our slopes look like they're 1s. And when we're looking at the negatives, we're getting more negative. And so, yeah, that looks pretty good. What's this Desmos link, I wonder? Wait, is it going to open? Oh, it's over here. Okay. So, this is a Desmos slope field generator. So if you plug in, and what did we have? X plus y. Then here we go. We have our isoclines on the line y equals negative x are all flat, and we have this one draggable isocline that we can use to see the slope anywhere, which is really fun, and I will link this somehow so that you can see it, but slope field generator is pretty cool. Hopefully we can get access to some software that lets us do stuff like this, but there's also, you know, good old Desmos. Very reliable. So that was our intro to slope fields, and be prepared to make connections between slope fields and differential equations. Be prepared to go from differential equations to sketching slope fields. It is a little bit more tedious than most people like, but you know, some people really like doing the whole like coloring thing. So there's sometimes it's nice to just have something kind of tedious to do with your brain and with your hands. Alright, so we're going to talk about Euler's method, and Euler's method is a way of approximating values. That's what we do. Alright, so this is from Hidden Figures. No copyright infringement intended. This is for educational purposes only. Alright, so Euler's method is looking at a way of approximating what a curve is going to look like, and the way that we approximate it is by basically making a bunch of lines. So we take an h value, which is a small change in our x's, and with that we can step through what our x values can be, and we find our y value using a line that the slope of the line comes from our differential equation. So you have a given differential equation. So you have a differential equation that is a function that uses both x and y, and you can find your next x value using your initial x value and add in some other h value. So h is going to be called the step size. And for the y values, which looks like it's in here, but this is a screenshot from the movie, and this is from, you know, book things. The way that you find your next your next y value is by looking at your initial y value. So you have x naught, y naught as the first point, and you multiply the h, which is the step size, by your function, your differential equation that depends on x and y, evaluate at your previous step. So Euler's method to approximate the particular solution of the differential equation y prime equals x minus y that passes through the point 0, 1. We're using a step size of 0.1. So our x values, well, our x naught is going to be 0, our y naught is 1, our x1 is going to be 0 plus our h step size, so 0.1, and then so on. We'll just keep on adding to those, and our y1 is going to be our initial y. y1 is initial y, which is 1, plus h, which is 0.1, times f of x naught, y naught, which is y prime equals x minus y, so x is 0, minus y is 1, and we get 1 plus 0.1 times negative 1, which is 0.9. And then we can find x2, which is 0.1 plus our h, which is 0.1, and we'll just keep on chugging along, find 0.2, and then y2 is y1, which is 0.9, oh my gosh, plus h, which is 0.1, times our f of x naught, x1, y1, which is 0.1 minus 0.9, and I wonder if we should use a calculator for this. Heck yeah! So let's use a spreadsheet. So we have this is our nth step. Here is my x values, where we're starting with the initial value 0 and 1 for x and y. That's slightly bigger. Okay, and then I put this $sign here because I want to lock in that I'm referencing the step size that I'm putting in right there. So $D, $2 gives us exactly that point, and I'm going to copy this down so I get all my x values. And look, my graph is taking that line. That's pretty cool. And then for my y values, I have my previous y value, C2, plus D2, which is my h value, times B2 minus C2. And B2 is my x value, C2 is my y value, so that is this section in the parentheses, that's my differential equation. So, calculated 0.9, which makes sense, that matches with what we had, and we're just going to copy that down. So, there you get 0.82, 0.758, and we're slowly, we're drawing a curve, aren't we? You see that over here? We're drawing this curve as we're finding our y values. It looks like a pretty nice curve. So let's go back over here. So our gray is the exact solution, and the black is our approximate solution using Euler's method. So it's pretty dang good. Like, look how close that is. It's pretty good. You get people on the moon or something. So what if you had y prime equals 2x over y? Well, if we want to find the general solution to this differential equation, what we need to do is separate the variables. So y prime is dy dx, right? That's old news. And that equals 2x over y. So we can separate our variables. We can push the y's to one side. So we have y dy, and then we can push the x's to the other side. We have 2x dx. We can integrate. On the left, we're integrating with respect to y, so we get y squared over 2 plus c, and we'll call it 1 just so that we have some distinction between our constants of integration, so we don't end up accidentally canceling things out. And then on our right side, we're integrating with respect to x, so we have 2x is going to integrate to x squared plus c2 because we're looking at a different constant of integration. Keep in mind, though, that c2 minus c1 or whatever like that is going to be some other constant of integration, so we are going to do that. We're going to push those together, so we get y2 over 2 equals x2, and let's call this plus c, where c is our just combined constants of integration. And now we have y squared over 2 equals x squared plus c. That's perfectly fine, but a lot of times we like to have c by itself. Why? Because it's just a helpful format. And sometimes we like to have the coefficient for y be 1, so we don't have this 2 hanging out, so we can know that that's equivalent to what this is, y squared minus 2x squared equals c. Just multiply by 2 everywhere, take that x squared and move it over. Alright, so if you are told that the rate of change of y is proportional to y, then you know the rate of change of y, dy dt, is proportional, so we're multiplying by k, that's something that you've thought about since algebra, and is proportional to y. So dy dt equals ky. That's helpful, because then we immediately know that we also have this exponential growth or decay model. So we have y equals c, which is the initial value of y, times e raised to the k, which is the proportionality constant, and a lot of times that's the thing we need to solve for, times t, which is the time that we're looking at, and we look at this in terms of time generally because things grow and decay with respect to time. Exponential growth and decay happens with all kinds of things. Radioactive things, happens with growing like bacteria, metabolizing different medicines or population models. These are all things that that follow exponential models. Might be interesting to look into more different things that follow exponential growth or decay models. Write about that in your journal. So growth happens when our k is positive, because that means that with our exponential function, we're going up. So that's when k is greater than 0. And we have when k is less than 0, we have an exponential decay. That's a really bad curve, I'm sorry. But that's going to be generally what our curve is going to look like, so we're decaying. If we want a proof of that, well, let's just take our derivative of y, and we get what? C times e to the kt times chain rule, k. But, look at that. C e to the kt, that's right there, that's y. So, we can rewrite this as y prime equals k times y, and I flipped this order around because of the commutative property of multiplication. Alright, so if we're given that the rate of change of y is proportional to y, when t equals 0, y equals 2, when t equals 2, y equals 4, what's the rate of change when t equals 3? So, we're given that the rate of change of y is proportional to y. That means that dy dt equals ky. That's what that means. So, we also immediately know that y equals c e to the kt. I wrote that there. Okay, well, it's right there. Hi, I'm tired. Okay, so we got that. And we have an initial condition. So that's actually our initial value, which is going to give us c. If you don't believe me, then just plug it in. 2 equals c e to the k times 0. K times 0 is 0, e to the 0 is 1, so c equals 2. So we can update our model. Y equals 2 e to the kt. And now we can use our other initial condition, plug that in, and solve for k. So 4 equals 2 e to the k times 2. And that's from our initial condition right there. We got that's not 1/2. That's 4 over 2. 4 over 2 is 2. And that equals e to the k times 2. Take the natural log of both sides. We got natural log of 2 equals k times 2. So natural log of 2 over 2 is k. And we're not done yet because we need to find the value of y when t equals 3. So we can update our model. Y equals c e to the 1/2 natural log of 2 power times t. Plug in, oh, we know c is 2, don't we? Okay, so now we can plug in 3 and we can get out a number. Here is the number. The thing that I don't really like about this answer is that there was a preemptive plugging into a calculator to find what this irrational number for k is going to be. This is a dangerous move because we want to save our approximating and our error happening for the very end. So be wary of doing stuff like that. If you're interested in how error compounds and all that stuff, take computational methods. That is a class that we offer at Blair, and it is a lot of it is about error and how to compute things. So if you haven't taken chemistry in a while, then this is the reminder that chemistry is a thing. So we have a list of the half-lives of some radioactive isotopes. And suppose that we had 10 grams of plutonium isotope that was released in the Chernobyl nuclear accident. How long will it take for that 10 grams to decay to only 1 gram? So how are we going to figure this out? Well, there's a couple of different ways, but here's the way that makes sense to me. Our 10 grams is going to become 5 grams in 24,100 years. So we can plug that in where we have 10 grams of our isotope, and then we have what, e to the kt power, but the t that we're looking at is 24,100 years, and that equals 5. So then we're solving for our k. And what do we get? We get e to the k times 24100 equals 1/2. So natural log of 1/2 equals k times 24100 divided by 24,100, and we get k. So I'm going to just say that k is natural log of 1/2 over 24,100. My goodness. Okay. So how long will it take for the 10 grams to decay to 1 gram? Well, we're looking for our initial amount of 10 grams times e to the, and I'm going to be lazy, I'm going to say k is the k that we looked at right here, times t. When is that going to be equal to 1? So e to the kt equals 0.1, and this is the answer. But to get there, we do what? Natural log of 0.1, and then divide that by the k, which is natural log of 0.5 over 24100, and you should get t, which is this big number, which is a very long time for that plutonium isotope to decay. Half-life. All right. Newton's law of cooling, and this one is these are the kinds of problems that get pretty tricky, especially AP, like College Board kind of stuff. They like to be tricky about this, so do be careful. Newton's law of cooling problems, just read the problem. So to model that, let's read the problem. Let y represent the temperature in degrees Fahrenheit of an object in a room whose temperature is kept at a constant 60 degrees. If the object cools from 100 degrees to 90 degrees in 10 minutes, how much longer will it take for its temperature to decrease to 80 degrees? So we're not looking for time. We're looking for time after the 10 minutes. So we're looking for time after once our object is at 90 degrees. And if you think about this, like, from your life experience, you might know that a room doesn't actually stay at the same temperature. But this is because we can't really handle more complicated things yet, which is totally fine. It's good to start where we can start. But we need to assume that our room is just going to stay at 60 degrees, which is a very cold room, but I digress. So, Newton's law of cooling is saying that, well, in general, that we have dt, where T is temperature, cap T is temperature. That's going to be equal to K, some proportionality constant, times the temperature of the object that's cooling, minus the temperature of the environment. The environment that the object is in, which in this case is a room that's kept at a constant 60 degrees. So, that is a good start. But Newton's law of cooling does use T, we're going to use Y, it's okay. So we have dy dt equals K times Y, which is the temperature of the object, and 60, which is the temperature of the room, which is the environment. Can't spell environment, sorry. So we have Y minus 60, and let's separate our variables and then integrate. So we have dy over Y minus 60 equals K dt. Integrate with respect to Y on the left and T on the right. And what are we left with? We got a natural log of absolute value of Y minus 60 equals K times T. And I'm going to be lazy and push all of my proportionality, or my constants of integration, over onto the right side. This is not advisable, but this is where we are right now. So here we can solve, because what are we given? Well, we're given some stuff. We're given the initial temperature is 0, at time 0 is 100. And we're also given that our temperature at time 10 is 90. So using that information, we can figure out what our unknowns are. So maybe we should, maybe we should start doing a little bit more algebra. So we have natural log of Y minus 60. Let's get that Y on its own. So let's solve for Y. So we have Y minus 60 equals E to the KT plus C. And now with exponent properties, we know how to handle that. We get Y equals, I'm going to push this 60 over. So we get E to the KT, and then if we're adding C in our exponent, that actually means that we're just multiplying by E to the C power, right? And that means, and then we're doing the plus 60 from here. But E raised to some power C, that's just going to be another number. So let's rewrite that. Let's just make our lives a little bit more simple. So we have c times e to the k t plus 60. And boom, there you go. Look at that. That looks very much like our exponential growth and decay model, because it is. But we are using the environment temperature as well. So using our initial condition of 0, 10, let's plug those in. So we get 0, 100, and so we get y is 100 equals c times e to the k times 0 plus 60. And so we get 40 equals c times e to the k times 0 is just 1. E to the k times 0 is just 1. So we have c equals 40. So we can update our model. Y equals 40 e to the k t plus 60. Now the only thing we don't know is our proportionality constant, but we have one unknown. We have another condition where we have 10, 90, and that we can plug in. So we get 90 equals 40 times e to the k times 10 plus 60. And then we can just solve for k. So let me see. So we have what, 30 equals 40 e to the k times 10. Those zeros can go away, so we get 3/4. And we divide by 4, so we get 3/4 equals e to the 10k, natural log of 3/4 divided by 10 equals k. So we can update our model one more time. Y equals 40 e to the natural log of 3/4 over 10 times t plus 60. And now the question was, what was the question? The question was, how much longer will it take for its temperature to decrease to 80 degrees? So we gotta look for the amount of time it takes to decrease to 80 degrees. So our goal is to find t, 80, kind of, but it's actually t minus 10, 80, but we'll get to that. So we have 80 is our y value equals 40 e to the natural log of 3/4 over 10 times t plus 60. So then we solve, and we got what, 20 equals 40 e to the natural log 3/4 over 10 times t. So 1/2 equals e to the natural log of 3/4 over 10 times t. Natural log of 1/2 equals natural log of 3/4 over 10 times t, and solve for t. And if you do that, because you have a calculator and stuff, then you get t equals, I think, something like 24 stuff, 24-ish minutes. But it's 24 minutes after the thing was 100 degrees. So our goal is actually to find the amount of time that has elapsed from when the object is 90 degrees to when the object is 80 degrees. And that was 10 minutes from, like, at time 0, we're at 100 degrees. At time 10, we're at 90 degrees. And then at time 24, we're at 80 degrees. So that means that the amount of time that has elapsed, the answer to our question is 24 minus 10, 14. So how much longer will it take? 14 minutes. Boom. All right. Cool. Cool.